In the fascinates for fascinates. I'm running a few points, and I can't really go 60. It's like, we have 2 weeks left. Well, not good finally. Finally. This is my show. It doesn't make sense because 526 is 626. I think this week 5 is actually final. 5 is. Sure can. I would. Just like our midterm this week. One week of, or next week we have the 2 midterms. After this week full. Done. Strategize. These next 2 weeks are gonna suck. Because both of them cumulative. Yeah, both cumulative, but in math, you said that he's gonna use 60% for the fund. Oh, yeah, I think I remember. So if you get 60% from the fund, I can't say then so well, where you from? That's cool. I had a quick question. When do you think you're gonna post the review for next Thursday's midterm?
Study guide probably be up. I need to see how far we get tomorrow.
Okay.
So probably after the lecture tomorrow.
After the lecture tomorrow.
Yeah.
Thank you. Cool. So we have again a week to study for this. Yeah. Really good study. It's cool. It's like it's not. Check. Good. You should probably do that. So. It just makes more sense. What happens if you didn't do food? No. Oh, okay. Even if there's a kind of When you scheduled to graduate? Sure. You just broke them. Just no fun. You know, yes, and you set up an album. So, how great you want to be. Just add 17 minutes. You're, that's your 60. No, well, 14%. It's fine. Since when? Been checking. It's normal, but yeah, that's what happened. And that's what I want. I want passive because I just want to meet and. Okay, because you're putting it very. 17. Um, and the so year to date, what? This is year to date. And you should. So this one's them. Your game should be based on general one. It's over. I, it's 5 or 6. So, it is a lot of. No, give this. You get all the same. That's really low. Yeah. Right reason. Yeah. Well, let's see. See. It's interesting, bro. Well, that's easy. Okay, that's good. There's a. I think change the two to entry bay in case super. Yeah, that. So. You have two to three, so make sure it's gonna be 2, 2, 3, 1. Make the same one, you just change this. Yeah. Oh, see. Change to.
All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. Happy Wednesday. How's everyone doing today? Good to hear. All right, so plan for today, we're just continuing on with control volumes. And so today should be the last day about control volumes. So after today, you should have everything you need to complete homework 3. So we have one more example in linear momentum. That's for moving control volume. So we'll finish that up today first thing. And then for the next part, I'm going to go a little bit out of order, just because I want to make sure I cover conservation of energy first and foremost. So we'll do that first, and then if we have time after that, then we'll do angular momentum. But we'll probably not do the full treatment for angular momentum, but it's a little bit more niche. It's still very important, obviously, but I think at that point we'll be sick of control volume. So yeah, today is kind of the last planned day for control volumes. All right, so remember homework 3 is due this Sunday. So after today, you should have everything you need to do it. That's going to be the only homework that I'm planning to test you guys on midterm 2 next Thursday. I usually don't like to I usually don't like to test you guys on things that I don't assign first for homework, just because the homework are kind of your chance to practice it and try it out. So tomorrow we'll do something new. But maybe we'll have the conceptual stuff on stuff for tomorrow. We'll see. But my plan right now is just to have the control volume stuff. Okay. So with that said, tomorrow I think I'll have after lecture tomorrow I'll have a strong idea in terms of where we are, and so I'll be able to put out a study guide for midterm 2 tomorrow. Okay. Any questions about anything before we get started for today? Yes.
When midterm 2?
Midterm 2 is next Thursday. Yeah, so not tomorrow, but Thursday. Yeah. Yeah, it was very quick. Yeah, we're halfway through for the summer already. It kind of feels like I just met everyone, but we're already kind of halfway through everything. So yeah. Any other questions before we begin? Okay, all right, so let's go ahead and continue where we left off. Okay, so we have just one more example that I wanted to do with the linear momentum. So let's go ahead and finish that up. All right, so specifically, we did a couple examples last time with conservation of linear momentum. We spent quite a bit of time discussing the details of those types of problems. The main caveat or kind of the main point I wanted to impart on you guys is the difference between the momentum velocity and the carrying velocity. Okay, and that's true even for moving control volumes as well. And so the last thing that we went over kind of right before we ended lecture yesterday was we had our Reynolds transport theorem for conservation of linear momentum or moving control. Okay, so we ended with this equation here. We have integral of W times the density times W dot N hat dA is equal to sum of all the external forces. Okay. Now, of course, this is assuming steady conditions. So I didn't write it here, but normally in Reynolds transport theorem, we have our accumulation term, the term with the time derivative. So that's normally there, but typically for momentum type problems and energy type problems as well, usually we ignore that term. So we only really concern ourselves with the inflow and outflow term. Okay. All right, and so of course, this is kind of a shorthand version of the equation here. Remember, we defined W last time, so this W hat. Okay. This is defined as the relative velocity. Right, where W vector is equal to velocity of the fluid minus velocity of the control volume. Okay. Right, so that W vector, that relative velocity is defined both for the momentum velocity and the carrying velocity. Okay. And just to remind you of that as well, right? Remember our two velocities here, the one that's inside the parenthesis here, where we're taking the dot product of it together with the normal vector. Remember, this is what we call the carrying velocity. And remember the convention for the carrying velocity. Carrying velocity, we typically only care about the magnitude of the velocity with the sign accounting for whether it's an inflow and outflow. Right, so remember for an inflow, we use a negative signs for the carrying velocity, and if we're at an outflow, we use a positive sign. Okay. Whereas this velocity in front right here, the one that's not within the parentheses without the dot product, this is what we call the momentum velocity. So for this one, remember, we're taking the components of the velocity vector. So that's the part there where if you have a velocity that is pointing in at an angle, we account for that angle here, right, with sines or cosines. And then depending on whether the velocity is going to the left or right, we use or up or down, then we use the appropriate sign there as well. Okay. All right, so I wanted to emphasize this again, just because this is probably the most important, probably the most confusing part of these control volume problems is what to plug in for these velocities, and it's one of those things where if you kind of try to overthink it a little bit, you kind of trick yourself into using the wrong sign or the wrong kind of convention for this, and so it's one thing one thing for me to be up here and say that the difference between these two is clear when I write it like this, but when you're learning it for the first time, it is very tricky. Okay, so definitely kind of ask yourself every time you do these problems, which one is the momentum velocity, which one is the carrying velocity, and what conventions do I use for each of them? Okay, because even though ultimately sometimes you're just gonna multiply by velocity twice, but there's some subtlety with the sign and nuance there. Okay, so make sure you kind of know what you're doing for that breakdown. Okay. Okay, so with that said, let's go ahead and do one more example. Right, so unfortunately, this example is a little bit contrived. So it's you know I mean you could see this in reality technically, but you know it's not something you see often. But we have basically a ramp with wheels. And so just like the first example we did yesterday, we're going to fire a jet of water at this ramp, and the ramp is going to redirect the direction of the water flow, and so that's going to create forces on our control ball. Okay. The only difference now is that since our ramp now has wheel, it is now free to move. Okay, so our ramp will be something like this. Right, so we have water that's coming in here. I guess technically it can be any fluid, right? And then it gets redirected up from the ramp up just like that. Okay. All right, so coming in, our velocity magnitude or our speed coming in is 100 feet per second. Our inlet area, A1, is equal to 0.006 feet squared. Okay. And then at the outlet, we assume basically the same thing. Right. So in that sense, you know, it's very similar to the ramp problem we did yesterday, where you know there's no reason for the flow to change cross-sectional area. There's no reason for it to change velocity, just because we're looking at a steady case. And so the outlet velocity and outlet area should be the same as the inlet. Okay. All right. But the big difference between this problem and the one we did yesterday is that now our ramp has wheels, right? So it's free to move. In fact, at this snapshot in time, we are going to assume that our ramp has a constant velocity, right? And so we're going to assume that our ramp is moving from the left to the right. And it's going to be moving at a velocity of 20 feet per minute. All right. And since we are using English units for this particular problem, we do need to express the density. Okay. So the density of our fluid is given by this, and so it is 1.94 slugs per feet cubed. Okay. So slugs is a strange unit, probably not one that you're using a lot unless you're working with British English units. So it's not literally slugs, right? So we're not measuring things in terms of snails or mollusks that we find on the ground. Slugs is just a unit of mass in English units. Okay. Okay. And so what do we want to find? So in this problem here, it's very simple. We want to compute. We want to compute the magnitude and direction of the force that the fluid is imparting onto the rim. All right, so a fairly standard conservation of momentum problem. How do I know it's a conservation momentum problem? Well, besides the fact that we're in that unit here. Okay. But whenever a problem asks you to find a force, right? The only way for us to obtain force in these types of fluid mechanics problems is to do conservation of momentum. Okay, so that's kind of a dead giveaway, you know, in these types of problems. Whenever the problem asks you to find force, then you have to use conservation of momentum. Okay. Okay. All right. So let's go ahead and apply our equation to this. So actually, this problem is actually quite short. There's not much. There's really not much to it. Okay. So in this case, since we already know the outlet velocity and we know the outlet outlet area, there's no need for us to apply conservation of mass. Okay. But before we plug into conservation of momentum, we first need to solve for the relative velocity. Right, so that's exactly what we're going to plug into our equation here. Okay, so in this case, the best place to apply this would be at the inlet. Okay, so at the inlet we have V1, right, minus VCV. And so in this case, they're both going to the right, and so they're both are positive, and so we just plug in the numbers for this. Okay, so V1 we're given as 100 feet per second, and VCV is 20 feet per second, both positive. And so that means our relative velocity here is 80 feet per second. Okay. Which also means that the relative velocity at our outlet is also going to be 80 feet per second. Okay. All right. So when we apply our conservation of momentum in the y direction or in the x direction, that's the w we're going to apply there as well. Okay. Okay. All right. So now let's go ahead and apply our conservation momentum. And remember, we have to do this in our two different vector directions. We have to apply it in the x direction and the y direction. So let's start with x. Okay. All right, we have fx is equal to integral w rho parentheses w dot n hat dA. Okay. All right, so just like we normally do in these RTT problems, we're going to evaluate this integral at both the inlet and the outlet. All right, so let's do the inlet first. Okay, so at the inlet, we have rho. Our momentum velocity is just W1 in this case. Okay. Our carrying velocity in this case is going to be a negative W1 because we're at the inlet. And of course, then we have A1. All right, and then we're going to do the same thing at the outlet. All right, so at the outlet, we have density again, right? So density is not changing in between the two inlets and outlets, so we're not considering the compressibility effects. Okay. Oh, I apologize. So there is one aspect of the problem that I did not give you yet, which is the angle of the outlet jet. Okay. Right, so it's given to us in the problem that the outlet jet here is angled at an angle of 45 degrees. Okay. So the ramp is basically redirecting this flow where it starts out all horizontal and then is pointing upwards at an angle of 45 degrees. Okay. Okay. And so at the outlet here, we first have our momentum velocity. So this is just the component or the x component of the outlet velocity. Okay. So this is going to be W1 cosine of 45 degrees. We're going to multiply that by the carrying velocity. Remember, carrying velocity, we don't care about the components. We only just care about the velocity magnitude plus or minus whether we have an outlet or an inlet. Okay? Since we're at an outlet, we're going to have a positive W1 over there. Okay? And we're going to multiply the entire thing by A1. Okay? Because that's the same outlet area, inlet area is the same. All right, and so we have everything here, so we can go ahead and plug in. And so Fx is equal to rho W1 squared cosine of 45 degrees times A1 minus rho W1 squared A1. Okay. We plug in all the numbers for that. We plug in for the densities. We plug in for the relative velocities. We plug in for the angle of the area. And what we get is a minus 21.2 pounds of force. Okay. Remember our sign convention, right? So remember when we solve the RTT for linear momentum straight up, this is the force that that is being placed on the fluid. Okay. And the sign here makes sense, right? Because if you think about it compared to inlet and outlet, right? At the inlet, we have our entire flow velocity going in the x direction, but at the outlet, that's redirected, so that some of it's going the vertical direction. Okay. So technically speaking, we're losing some momentum in the x direction. So it makes sense that our force is pointing in the negative direction because we are, using that to reduce the momentum there. Okay. But the problem asks us to find the force that the fluid is imparting onto the ramp. Okay. And so if this is the force that the ramp is putting on the fluid, then the force that the fluid is putting on the ramp is equal and opposite in direction. Right. And so the force that the fluid is putting on the ramp is a positive 21.2 pounds going in the positive x direction. Okay. Good. All right. Any questions on that part right there? All right, so moving control volumes, not that difficult. The only thing you just have to be aware of is just computing the relative velocity. Okay. Now you have to be careful a little bit. And so when you're computing the relative velocity, notice how I computed W here from the inlet, right? Because at the inlet, the velocity and the fluid velocity and the velocity of the control volume are going in the same direction. Okay. And so in those situations, it's a lot easier to compute the relative velocity. Whereas if you did it from the outlet, right? So technically you can do it from the outlet as well. But at that point, you only need to compare the x component of the outlet velocity, which is not impossible, but is still just a little bit more inconvenient. So I would definitely recommend, look at your geometry, look at your system, try to find the velocity or either the inlet or the outlet where the fluid is going in the same direction as your control volume and use that to compute your relative velocity. It just kind of makes your life a little bit easier. Okay. Okay. All right. So let's do the same thing, but in the y direction. Okay. All right. So we have Fy is equal to integral W rho W dot n hat dA. Okay. All right, so just like we did for the x direction, we're going to evaluate this integral, one term for the inlet, one term for the outlet. Okay. Right, the only difference is that we're looking at the y components now. Okay, so at the inlet, we have our fluid density rho. Okay. Our fluid velocity at the inlet is completely in the x direction. So the y component at the inlet is actually going to be 0. Okay. We're multiplying that by its carrying velocity, although technically it doesn't matter now because we have a 0. So let's just write out the rest of it just in the interest of completeness. Okay, so remember for the carrying velocity at the inlet, we have a negative W1, and then we're multiplying that by A1. Okay, okay, and then we're going to add to that the contribution at the outlet. Okay, and so at the outlet, we have rho. Momentum velocity, we have a W1, remember that's pointed upwards in the at an angle of 45 degrees. And so vertical component is going to be W1, sine of 45. Carrying velocity here is W1 times A1. Okay, all right, and so we just go ahead and plug in for this. And so Fy, which is the force that the ramp imparts onto the fluid, is equal to rho W1 squared A1 sine of 45. Okay. We plug in the numbers for that, we get 52.6 pounds. Okay. Okay. And then we're going to do the same thing we did in the x direction. So if this is the force that the ramp is imparting onto the fluid, then the force that the fluid imparts on the ramp is the same magnitude but opposite in direction. Okay. So Fy equal to minus 52.6 pounds. All right, and so those are our two force components. Okay, so we have a positive 21.2 pounds in the x direction and a negative 52.6 pounds in the y direction. Okay. All right, so we're almost done. So specifically for this problem, so these are the components of the force, but specifically in this problem, they asked us to find the force magnitude and force direction. Okay. All right, so if we treat these as components for a vector, right? So our force vector is equal to 21.2 pounds, comma, minus 52.6 pounds. Okay. This first component is Fx, second component is Fy. All right, so our magnitude, and we're just going to use our good old kind of magnitude formula here. So we're going to take the square root of Fx squared plus Fy squared. All right, so we plug in for that, we get 57.3 pounds. All right, and for direction, so there's multiple different ways to express direction. But typically, I think the most straightforward way is to use the polar coordinates, definition. So we find out the angle that this force vector makes with the horizontal. Okay. Okay. And so the direction, based on our components here, we're going to take arctangent of Fy divided by Fx. Okay. Because essentially, what we're doing, if this is the positive x-axis, okay, and let's say that our force vector looks like the following. Right, we're essentially solving for that angle right there. Okay. Fx is like this, and Fy is like that. Right, so we're solving for the angle of a right triangle that's formed by our force components. Okay? All right, so we plug in for that. Right, so you can solve this in radians or degrees, it's whatever personal preference that you have. But my solutions are in degrees, so we have a minus 68.05. All right, any questions on that? Okay, all right, so that's conservation of linear momentum. So we did spend quite a bit of time on this. It may not seem like it because it was just yesterday and the summer goes really, really fast. But I did want to take my time with this part because it is, this is kind of the part where I think it gets confusing. So what's left for control volume analysis here, first of all, is conservation of energy, which, when you look at it on the surface, it seems more complicated than momentum. But I think once you get the hang of momentum, energy is actually a bit more straightforward, just because it's not a vector. And then if we have time, second half today, we'll do conservation of angular momentum as well. Okay. Okay, well, let's start with conservation of energy. Okay, so we have conservation of energy in control volumes. Okay. Okay, so this is not our first time seeing conservation of energy, right? So kind of right before we started all of this nonsense with control volumes, we went over the Bernoulli equation, right? So the Bernoulli equation at the end of the day, is essentially an expression of conservation of energy. But, there was some caveats to using a Bernoulli. Okay? So there were a lot of conditions to using Bernoulli, right? So first of all, we had to look at a steady situation. Our 2 points that we consider has to be along a streamline. We have to be incompressible and we have to be inviscid. Okay. So one of the main upshots for this, and this was an exam question as well. So and a lot of people got this right on the exam, by the way. But Bernoulli's equation is, at the end of the day, cannot account for any types of energy losses or any energy dissipation. And that really is kind of a big weakness because dissipation and losses are part of just every single mechanical device or every single type of system. Okay, it's impossible to create an engineering device with perfect efficiency, right? You're always going to have some losses because of friction, because of just inefficiencies of the thermodynamic process that we're going through, right? And so and those losses always have to be accounted for. Okay. With control volume analysis, control volumes are a bit more of a general kind of framework. And so it does give us the ability to account for these types of losses, as well as other types of inputs as well. And so we can also consider things like, maybe we're adding energy to the flow from like a pump. Maybe we're looking at a turbine-like device where we have a device that's extracting energy from the flow. Maybe we're heating the flow in a certain ways, right? So control volumes kind of give us a way to do all of this. So that's kind of the theme here, and that's kind of the theme of control volume analysis in general, where control volume analysis is very general, right? And so probably you've noticed at this point there are a lot of nuances and a lot of details and a lot of kind of rules about the signs and everything that go into control volumes. The reason for that is that control volumes is so flexible. You can use it for lots of different types of scenarios, and the same goes for conservation of energy as well. Okay. Okay, so we're going to approach this the same way that we've done conservation of mass and conservation of energy, or excuse me, conservation of mass and conservation of linear momentum. So we're going to start with the general form for Reynolds transport and then apply that directly to conservation of energy. Okay, so let's start with our general form for Reynolds transport theorem, and I will go ahead and we'll write out the full form of Reynolds transport, just because yesterday I know we didn't do that. So let me go ahead and write that here. Okay. Okay. All right. So the full form of Reynolds transport theorem in terms of a general flow quantity B, right? So we have the material derivative of our quantity B in our system. Okay. Remember, so this was our production term. This term can also be used to account for depletion as well. And so that will be kind of a big theme today. Because there are ways for energy to leave a system, whether it be through heat, through viscous dissipation, or maybe it's intentional. Maybe we have some kind of turbine, like a windmill or something like that, where we're intentionally extracting energy from the flow. Right? This is equal to partial T integral B times rho dV. Right? So this is our accumulation term. And then finally, we have the term which has given us the most action up until this point, which is the inflow-outflow term. Okay, so we have integral B times rho, and we're just going to look at stationary control volume for now. So we have velocity of the fluid, dot product with n hat, our carrying velocity dA. Okay, and this right here is our inflow-outflow term. Okay, so that's the general form for Reynolds transport theorem that we've been working. Okay. Okay, where B. And so capital B here, remember, this is our general extensive property. Right, so remember what an extensive property is. An extensive property is some kind of property of the fluid that changes with the mass, right? So the more fluid we have, capital B tends to go up. Okay. And then little b here is the corresponding intensive property. So we basically just take our extensive property, we divide it by the mass. Okay. All right. So just like we did with conservation of mass and momentum, the way that we basically apply Reynolds transport, we have to do two things. Okay. So number one, right, we have to plug in a specific expression for little b. Okay. And whatever we plug in for little b, remember, that has to be some kind of conserved quantity. Okay, so there has to be some conservation law that governs that quantity, right? So we have conservation of mass, conservation of momentum, and now we're going to have conservation of energy. Okay. Right, so that's the first thing we're going to do. And then second thing we're going to do is we're going to plug in an expression for the production term. And that's going to depend on our choice of little b. Okay, so we're going to do both of those things to this expression here. Okay. Okay, so let's start with step one. So let's plug in an expression for little b. Okay. So the theme here is energy. So our little b here is going to represent the total energy, or I would say intensive energy of our fluid. Okay, so little b. This is going to look very familiar because you're going to see in a second. Okay, so little b here we're going to have the pressure divided by the density. So be careful here, both of those symbols look similar, right? So pressure is a P with a little ponytail, and then density is a rho, which is a lowercase p that's kind of slightly tilted. Okay. Next, we have our velocity contribution or kinetic energy. So you have v squared divided by 2. Okay. Okay. Remember, we've essentially divided by the mass, right? And so that's why this takes a slightly different form than the Bernoulli equation. Well, just kind of spoiled it a little bit, although maybe I've already spoiled it. Okay. Next, we have our potential energy term, which is just the gravity multiplied by z. Okay. All right, so this looks very familiar. But we do have to account for one additional term here, which essentially is the temperature of the fluid, although we're going to express it in energy terms. So that last term that I've added there is what we call the internal energy of the fluid. Okay. So internal energy is it's kind of almost like a catch-all term that we use. Technically speaking, internal energy can refer to lots of different types of energy within the fluid. It can technically refer to things like chemical energy if you have some kind of fuel, so let's say gasoline. But for the most part, internal energy is essentially the temperature of the fluid. Okay, just expressed in energy terms, right? So most of the time, the biggest contribution to internal energy, unless you have some kind of fuel, is temperature. Okay, so we're now basically accounting for that here. Okay, and so we're going to take this little b, we're going to plug it into our Reynolds transfer theorem here. Okay, all right. So that's pretty straightforward, especially given the fact that a lot of these are very familiar faces. So we have all three contributions to the Bernoulli equation here. We have our pressure term, kinetic energy, potential energy term. Okay. Okay. And then to complete our derivation or to complete our expression here, we need to plug in something for the production term. Okay. Okay, so for production term, we're going to sum it up in two different contributions. One contribution for thermal contribution, so any kind of heating or cooling that occurs, and another for mechanical work. Okay. And so what we're gonna have is we're gonna have D. Technically, we're looking at total energy now. So technically E of the system, dt is equal to Q dot net plus W dot shaft. Okay. All right. Where this Q dot, which I know is confusing. I know we use Q for volumetric flow rate, but this is Q dot. Okay. So the Q dot here is the heating or cooling. Okay. Heating or cooling is going to cause heat transfer, and so basically energy transferred through heat transfer to our fluid. Okay. So if you're looking at specific devices that are meant to exchange heat, so something like a heat exchanger, maybe something like a radiator, maybe something like a some kind of cooling. If you're doing electronics cooling, this is something that maybe this is the heat that's coming from your computer parts and going into the airflow or water flow. Okay. Yeah. And then we have W dot shaft here, which is just the general term that we use for mechanical work. Okay. And we can actually use this mechanical work term to account for both work that's done on the fluid or work that the fluid does onto a device. All right, so that's so in general, we can kind of split our energy production into these two terms. Okay, where technically it's true that by conservation of energy, it is impossible to create or destroy energy, right? So energy is kind of the same as mass. We can't just create it out of nowhere or delete it forever. But energy is able to change form, and it is able to kind of leave and enter a system kind of a lot more easily than mass. Okay, so when I say production of energy or depletion of energy, that's not saying we're creating energy out of nowhere or just deleting the energy. Usually when I say producing energy, what I mean is we're converting energy from another form and putting it into a form that's useful for the fluid. And energy depletion is the energy is somehow changing form from the fluid and it's transferring out through some form that's not consumed. Okay, good. All right, so one assumption that we'll typically make, just because this is a fluid mechanics class, and so we're not getting into heat transfer. That's the next class after this. We're going to most of the time neglect any contributions from Q.net. Okay. So we're not going to have to worry about heating or cooling of the fluid just because this class, again, this is just pure fluid mechanics. Okay. This will be something that you do in the next class, but for now, we'll ignore this. Okay. Okay. So that's useful, and that way we don't get confused with Q, right? Because Q, remember, we're already using for volumetric flow rate, so there's no need for us to get confused with another one. Okay. So if you're curious about what this assumption is, this might be a term that you remember from thermo, but we're basically making what's called the adiabatic assumption. All right, so that takes care of that term. So that's one that we don't have to worry about. Now for the shaft work, there's kind of two different ways that shaft work can affect our fluid, or at least two different ways that we'll consider in this class. Okay. And so on the one hand, we're going to have shaft work, which is done on the fluid, which is essentially adding energy to the fluid flow. So this will be situations where we're doing mechanical work on the fluid. Maybe we want to increase one of the other fluid energies, right? So maybe we want to pressurize the flow. Maybe we want to increase the velocity of the flow. Maybe we want to increase the height, right? Maybe we just want to just pump the fluid up from a lower elevation to a higher elevation. That's very common. You see that in your house. You see that in this building here. Okay. So for situations where we're having work done on the fluid, we call these pump-like devices. Okay. Because a pump is the general term that we use for devices that add energy to a fluid in some way or form. Okay. And most times either going to be to pressurize the flow or to increase its speed. Okay. Okay, and then the opposite that can occur is maybe we're having the fluid do work on the object, right? So we're extracting energy from the fluid. So if the fluid is doing work on the object, it's essentially removing energy from the fluid flow in order to use that energy for something else usually. Okay, so you'll see this a lot in energy production. And so a windmill is a perfect example of this. So a windmill basically takes wind energy, converts it into mechanical energy, and then mechanical energy is usually converted to electrical energy that we can use to power our lights and stuff. Okay. So these types of devices, which are devices that are meant to extract energy from a fluid, these are called turbine-like devices. Right, so that's kind of the general term that we use for these types of devices here. Okay, and so we'll do examples on both, but I do want to kind of make that distinction now. Okay, all right. Any questions on this so far? Okay, all right. So let's go ahead and let's put it all together. So let's put this all into one kind of form for Reynolds transport. Okay. I will make one additional assumption here, which is the assumption we made for linear momentum, in that we are going to assume steady conditions. Okay. So remember, under steady conditions, we are going to neglect the accumulation term. All right, and then we do all that. We are left with the following expression for conservation of energy in a control volume. All right, so what we're left with is integral, right? We have our entire expression for the total energy. We have P divided by rho plus V squared over 2 plus GZ plus the internal energy, okay? Multiplied by the density rho, multiplied by our carrying velocity V dot N. VA. And this is equal to our shaft work. And that's our expression for conservation of energy for a control volume, okay? Given that we've already made assumptions under steady conditions, and we've also made an assumption of adiabatic flow, so there's no heat transfer that's going to occur. Okay, good. All right, so looking at this expression here, it looks like Bernoulli's equation, but just, more complicated just for no reason, right? So, that's not a coincidence. And so first couple of examples we'll do today is we're just going to look at just this equation just by itself. And then probably after the break, we'll probably look at this compared with Bernoulli's equation. Okay, so let's do our first example. Okay, so for this example here, we're going to look at a simple pump, and we're going to do our conservation of energy. All right, so remember, a pump is a type of device that adds energy to the flow in some way. Okay, so that means that, relative to the inlet, our outlet flow, we're expecting to have, some higher energy, either higher pressure, higher velocity, maybe higher elevation, higher potential energy. Sometimes we'll have higher internal energy, but usually that's not that useful. There's more effective ways to heat a fluid than just by pumping it. Okay. Okay. All right, so let's see. So we have a simple device like this. So we have an inlet here. Okay. That's going to come to the main pump body. All right, and so to add energy to the flow, we have this basically like a fan that's on the inside, but we're forcibly kind of moving this fan. Okay, so there's our fan. Our fan is rotating here. So let's say this fan is attached to a motor. And so that motor is constantly moving. It's going to be pushing the flow through the device. And then the flow is going to come out just like that. Okay. All right, so let's put some numbers here. So let's say that our inlet diameter, okay, so we have D1 is equal to 6 centimeters. Our outlet diameter, DO, is equal to 2 centimeters. Okay. All right, so right away you can see just by the shapes of our inlets and outlets, and just by conservation of mass, we do expect the velocity of the fluid at the outlet to be greater, just because of the size of the outlets there. Okay. All right, we're also given the pressure at the inlet. Okay, so P1 is 125 kilopascal, and P2 here is 450 kilopascal. Okay. All right, so we're actually given the solution kind of right away from this pump. We're kind of given the purpose of this pump right away. So this pump is mainly there to pressurize the flow. Okay, so we have fluid that's coming in at a low pressure. It's coming out at a high pressure. Okay. Typically, that's not the case, right? So if you have a typical flow in a pipe, pressure usually goes from high to low, right? But because we're going from low to high here, the only way that can happen is because of the pump. Okay. We also know the volumetric flow rate of flow coming in, right? And so we're going to assume that flow is coming in, Q in is equal to 0.02 meters cubed per second. Okay. So we can use that volumetric flow rate together with the diameters in order to get the velocities. Okay. All right. And so in addition to that, we are given some additional assumptions. All right, and so in the text for the problem, so I'm just paraphrasing here. Normally there's a paragraph that kind of, tells you these things, but, I'm not going to write a paragraph in right now. Okay, but basically in the problem, it tells you to assume steady conditions. Right? Although we kind of already knew that just because otherwise we wouldn't be able to analyze it. Okay. We're also going to assume adiabatic conditions. Right, so there's no heat transfer that's occurring here, so we can just purely focus on the mechanical work. The problem also tells you that you can assume that there's no change in temperature for the fluid. Okay. Now we can interpret this by saying that the internal energy of the fluid does not change from inlet to outlet. Okay. So that's our assumption. So let's find out what we're computing. Okay. Okay, so from this problem, we are looking for, we want to find out the power consumption of the pump that's needed to drive this flow. So essentially, in our conservation of energy equation, we're going to solve for W dot shaft. Good. Not have the density. Sorry, we're going to see if we got the density. All right, so in this case, we don't have the density, but it's going to cancel out kind of later on once we plug it in. All right, any questions on the problem setup? So there's you know, this is a relatively simple problem, but there is a lot going on. Any questions on just kind of anything that we see in this figure here? Okay. All right, so let's go ahead and start solving. Okay. All right, so we know just based on the problem and based on what we're trying to solve for here, we do need to apply conservation of energy. So there's no other way to compute power consumption or energy consumption. Okay. But before we do that, let's apply conservation of mass, just because that's always kind of a good step to do. Okay. Because if you look at this problem, there is something that's missing here that we need before we can apply conservation of energy, which is the inlet and outlet velocities. Okay. So conservation of mass is always a great way to solve for the velocities. Okay. And most of the time, you know, if you're missing some velocities or you're missing something, you know, conservation of mass is kind of the way to go. Okay. Okay. All right. So the way I'm going to do this is a little bit different. So, you know, what we've done, you know, for over the past, you know, couple lectures is that, you know, we've gone straight from the Reynolds transport expression for conservation of mass. But this time I'm just going to reason through it just by kind of logic. Okay. All right. So what we know. So from this problem, we know that we have just a single inlet and a single outlet. Right? And so what that tells us is that all the fluid that comes in from the inlet has to leave the outlet, right? Because we've already assumed that steady conditions. Otherwise, there's you know, you would have either accumulation or depletion of fluid, which we know is not possible because we have steady conditions. Okay, so we're given in the problem, we're given that flow comes in at a volumetric flow rate of 0.02 meters cubed per second. And what do we know? We know that volumetric flow rate is equal to velocity times the area, okay? Times the cross-sectional area. Okay. All right, and so based on that, we can compute the velocity. Okay, we can do this for both the inlet and the outlet. All right, so velocity at the inlet is equal to Q divided by A in. Okay, and velocity at the outlet is equal to Q divided by A out. Right, where area inlet and area outlet can be found just based on the diameters that were given to us in the problem. Okay. All right, so we go and plug in for that. We know area is pi over 4 diameters, diameter squared. And so at the inlet, we have a velocity of 7.07 meters per second. And at the outlet, we have 63.66 meters per second. Okay. Okay, so this is a way we can use conservation of mass. Okay. So, I know, for the most part, for this class, I do try to stick with the same procedures. I try to, stick with the equations as much as I can. But I don't mind that you guys would solve something like this via kind of logic. Okay, just because this question kind of came up in office hours today. And so if you can kind of justify your methods here and your explanations are clear, feel free to kind of take a little bit of creative liberties with the equations and do something like this. Okay. Now this isn't that creative, right? And so we're just using our flow rate equation, but you don't have to use the full Reynolds transport every time. If it's a pretty obvious case here with a single inlet, single out. Okay. Just for your future reference. Okay. Any questions on this so far? Okay. All right, so now that we have the velocities, we are now ready to apply conservation of energy. Okay, so let's write out this time I will write out the full Reynolds transport just as this is our first time. Okay, so our full Reynolds transport here is we have integral of pressure divided by density plus V squared divided by 2 plus GZ plus internal energy times rho times velocity dot n hat EA is equal to W dot shaft. Okay. And you can see I've already made the cancellations for adiabatic flow and for steady flow. Okay, so there's no accumulation term, there's no heat transfer term. Okay, so in other words, we just have the inflow and outflow contributions. Okay, so we're gonna basically evaluate this at the inlet and outlet. Remember, keeping in mind the sign convention for the carrying velocity. Okay. Okay, so let's do the inlet first. So at the inlet, we have P1 divided by rho plus V1 squared divided by 2 plus GZ1 plus internal energy at location 1, okay, multiplied by the density. We're going to multiply that by a negative V1 because remember we're at an inlet, so the carrying velocity is negative, multiplied by A1. Okay. Okay, and then to this, we're going to add the exact same thing at the outlet. So at the outlet, we're going to have all the same terms except everything's going to have a subscript 2. All right, so P2 divided by rho plus V2 squared divided by 2 plus G D2 plus internal energy at equation 2 times rho. This time we have a positive V2 because we're at an outlet. Multiply by A2. Okay. All right, so next thing we're going to do is we are going to cancel some terms here, okay? Based on the assumptions that we made in the problem. Okay, so first thing we're going to do is that we are given in the problem that there's no change in internal energy, okay? So that means the internal energy at the inlet and outlet are the same. Okay, so we can go ahead and cancel those two terms out there, okay? All right, next thing that we can cancel out, which wasn't given to us in the problem, but we can kind of just guess just based on the figure, right? There's no change in elevation, right? So the height or potential energy at the inlet is same as the potential energy at the outlet. Let's go ahead and cross those ones out as well. Okay. Sorry, I was kind of looking ahead. I think this problem does have a density. I think I just forgot to write it down in the notes. But this should be an example from the book. So there should be a density that's given there. Okay. Okay, because we do need to plug it in. So even though the density does cancel on the pressure term, it does not cancel on the kinetic energy. Okay. Okay, so let's go ahead and plug everything in. Okay, or let's write out the simplified expression first. Zoom back in. Okay. So simplified, we have P2 divided by rho plus V2 squared divided by 2 divided by rho V2 A2 minus P1 divided by rho plus V1 squared divided by 2 rho times V1 A1. Okay. And all this is equal to W shaft. All right, so assuming that you have the density, assuming that I gave it to you, and so problems that I give you for homework and exam, we'll have everything that you need. Okay, but at this point, we have everything that we need to plug in. Right, so you punch that into a calculator, we get W shaft equal to 46,530 watts. So what you should see from this problem is that the outlet should have more energy than the inlet. Okay. And the only way that's possible is because the pump is exerting energy on the fluid. All right, any questions on this? Any questions on this example here? Okay, questions.
So for this case, if the I guess for the velocities, they would have a sign according to the coordinate system.
Actually, so yes. So
Just positive, right?
actually no, so technically they would, yes. But since we're squaring it, then that kind of eliminates the sign there.
Okay.
Yeah, so you could have velocity going in the opposite direction, but the sign will cancel out because we're squaring it. And then carrying velocity has its own sign convention for inlet and outlet. Yeah. All right, so I saw a question from the chat. Okay. All right, question. So isn't work in joules? Is there a conversion that happens to power? Yeah, no, you're right. So work is typically in joules, but what we're solving for here is W dot with a dot on top. And so that dot there means time derivative. So we're looking for power in this case. Yeah. Yeah, so I'd have to work through the units, but you should get power from this expression here. Because there should be an extra time dimension that should end up in the denominator. Yeah. Because you have velocity squared times the velocity, so that's three dimensions of time in the denominator, and I think the pressure cancels out with two of them. So you should end up with one extra time component in the denominator. So that gives you power. Yeah, good question. All right, any other questions before we go for break? Okay, all right, so let's take a break. I do have quite a bit more I want to cover today, so let's come back in 10 minutes. So let's come back 4:27. 4:27, yeah. Okay.
You're teaching the Fullerton in fall, right?
Yes.
Are you teaching section one?
There should only be one section on 410 in the fall. Is there two?
I think there would be one.
Okay, yeah, usually there's only one, but yeah, I should be teaching them.
You know if you're able to take people from weights?
I'm not sure what the situation with that is. I usually for that class, so that class is taught in here. So in this class, I think technically there's like 60 something chairs. I can't teach 60 students. That's kind of crazy. But typically for that class, I can handle around 45, 50 students. And so I don't know how many people. I know Dr. James was already kind of expanding the number of seats in the class. So I don't know how many seats there are right now, but the total number of students I will take in that class is like 45, 50. Probably closer to 45. But I do plan on teaching 410 in the spring as well. And so if you do miss out on the fall, then it should be there in the spring.
Someone will do this from now on the provide schedule.
Gotcha.
I just applied for the e-transfer,
Mhm.
but that's on like Mondays and Wednesdays.
Yeah.
Early in the morning, so.
Oh, okay. Gotcha.
Yeah.
Gotcha. Okay. Yeah. I don't know who's teaching the heat transfer class, but yeah, finite elements, I'll be teaching it. Yeah, total number of students will be 45. So you can check the registrar's website, you can check the schedule of classes, and see how many people are in the class right now. And then just go based on that.
Yeah. Oh, so someone was. Magic. First movie. So, 6. Here,
All right, it's 4:27, so let's get back to it. Okay, so all I have planned for the rest of today is just more examples for the most part. There is a little bit of comparing this method to Bernoulli. And in fact, this will actually lead to a modified version of our Bernoulli equation to account for losses. But for the most part, we're just doing that. And I think we will have time to do a little bit of conservation of angular momentum, at least enough to do the homework plan. Okay, because I was looking at the homework problem today, so problem 5 on the homework does require a little bit of conservation of angular momentum, and so I do want to make sure that I cover enough to do that, but we're probably not going to do the full treatment of angular momentum. Okay. Okay. So that's kind of the plan for the rest of today. So let's go ahead and do another example of conservation of energy. Okay, so so the first example that we did was an example of a pump, right? So a pump we know is a device that adds energy to a fluid in order to increase its energy, right? So in order to increase its pressure, increase its velocity. In this case, we increase its pressure, in some way, shape, or form, right? So this next example, we're going to look at the opposite type of device, which is a turbo. Okay. So remember, a turbine is the opposite. So a turbine will seek to extract energy from the fluid in order to turn that into some other type of energy. Okay. All right. So what you're going to see for a turbine is that, unlike the previous example where the flow exits with more energy than the inlet, with the turbine, the flow is going to have less energy than it did at the inlet. Okay. Okay. So we're just going to do, this is kind of just a contrived example here. So we have a turbine that maybe looks something like this. It's like a funnel. Right, so a more traditional turbine will be something like a windmill, something like something that has some kind of spinning blades. Where instead of the previous example where we're forcibly moving the blades of the fan with the motor, typically for a turbine we're letting the blades of the fan kind of move passively along with the fluid. Okay, so imagine that there's some kind of there's some kind of fan or there's some kind of device on the inside that's turning in response to the fluid. Okay. Okay, so at the inlet here, right? So first of all, we have the inlet area. So we know inlet area is 0.01 squared. And then going into the domain, we have U1, right? So velocity is coming in at 30 meters per second. So this is probably some kind of air turbine, right? So 30 meters per second is pretty fast. So that's having water moving that fast is probably pretty dangerous. Okay? We know the pressure at the inlet. So pressure at the inlet is 600 kilopascal. And we know the internal energy at the inlet as well. Okay. So the internal energy at the inlet is 3,350 kilojoules per kilogram. Okay. Okay, and then at the outlet. Oh, actually, we do have water in this case, surprisingly. Okay. And at the outlet, we have an outlet area, A2 is equal to 0.02 meters square. Okay, so it's twice as big. Velocity at the outlet is going to go down. The velocity at the outlet is 20 meters per second. Pressure at the outlet is 500 kilopascal. And then the internal energy is going to be 2,500 kilojoules per kilogram. Okay, so across the board, all the types of energy except for potential energy are going down, right? So velocity is going down, pressure is going down, internal energy all going down from inlet to outlet. Okay, now some of that, so the velocity differences, you can probably account for the fact that our areas here are different. But there is going to be a sense of other energy that gets extracted. Okay. Okay. And so based on this, we have energy leaving the system, right? So we have some mechanical work leaving. Okay. And that is what we're going to solve for. So we're going to compute. Okay, so we're going to compute the energy the energy that's generated from this flow or from this turbine. Okay, we're going to make a lot of the same assumptions that we did in the previous example. So we're going to assume that the flow is adiabatic, so there's no heat transfer contributions. We're going to assume that the flow is steady, so there's no accumulation term, and then we're also going to assume that there's no change in height, right? And so, but that's kind of implied from. Okay. All right, and this time we do have a density, before I forget. And so the density in this case is 1,000 kilograms per meter cubed. Okay, so we're working with water. So I said, this water is unlikely just because of how fast it's going, but I guess this is kind of a big turbo. Okay, good. All right, so in this case, we have another situation where we have the velocities at the inlet and outlet already. So since we already have the velocities at the inlet and outlet, just like the very first example we did today with the ramp, there's no need for us to apply conservation of mass. Because normally you would apply conservation of mass in these cases to solve for any kind of missing velocities that you have. But in this case, we're given everything, and so there's no need for us to do that. Okay, so we can just skip right to conservation of energy. All right, so let's go ahead and write that out. So under our assumptions of steady flow and adiabatic, then our conservation of energy simplifies to the following. Okay, so we have P divided by rho plus V squared over 2 plus G times Z plus the internal energy multiplied by rho times V dot N EA is equal to W dot shaft. Okay. And so just like the previous problem, we were solving for that W dot shaft or the mechanical work. Okay. But in this case, that mechanical work is going to be negative because that's energy that's leaving the fluid. Okay. Okay, so just like before, we are going to evaluate our inflow outflow term at the inlet and outlet. Okay. And so at the inlet, we have P1 divided by rho plus E1 squared divided by 2 plus GZ1 plus E1, okay, times the density times a negative V1, right, because we're at the inlet times A1, okay. And then to that, we're going to add everything's all the same quantities at the outlet, but our carrying velocity at the outlet is positive because it's an outlet. Okay. We have P2 divided by rho plus V2 squared divided by 2 plus GZ2 plus E2, okay, times rho times positive V2 times A2. Okay. All right, so we have everything in this expression here. The only term that we're going to cancel out is the potential energy term because we're assuming that the height of the inlet and outlet is the same. Okay. Seems like we're always canceling out that term, but last example that we have in conservation of energy, I promise you there we are going to do one change in height problem. Okay. All right, so we plug everything in, right? So this is just actually just a very simple plug and chug, right? And then what we get from this is W shaft is equal to negative. Let's see, 5.035 times 10 to the 6th watts. Okay. All right, so fairly simple problem, but I did want to highlight something here. Right, so of course, we got a negative here. And the reason we got a negative is because we have fluid, we have energy that's leaving the fluid. Remember, and this kind of continues our theme from linear momentum as well. So the sign convention that you get from the production term, whether it be the summation of the forces from conservation of momentum, or the power that we get from conservation of energy, right? The sign convention tells us whether the force is being added. It's remember that the sign convention tells us what's happening to the fluid itself. Okay. Right. Whereas in the previous example, right, we ended up with a positive shaft work or shaft power. That's because energy is being added to the fluid. Okay. And so this means that if you have a turbine-like device, for turbine-like devices, the shaft work or the mechanical work will be negative. Whereas pump devices will have a positive shaft work. Okay. So that's something to keep in mind, right? And so if you have a problem where it's either a pump or turbine, but you get a mechanical work that's the opposite sign, that's usually kind of a good symbol or a good sign that you need to probably go back and check your work. What is it? Okay, maybe you plugged in something incorrect, right? Because this should always be the case here. Okay. All right. So any questions on this example before we kind of move on from here? Okay. All right, so I have a couple more examples with conservation of energy, but before we do that, let's go ahead and take a step back and let's compare this to Bernoulli. All right, because remember, when we talked about Bernoulli, I guess it was just last week. This summer's going so fast, right? We essentially said that Bernoulli is an expression of conservation of energy. Okay, but in this case with control volumes, we're actually doing conservation of energy. So let's compare the expression that we have now compared to Bernoulli. Okay, so let's start with Bernoulli equation first. Okay. And so let's assume that all of our assumptions with Bernoulli are the same. Okay. Right. So with Bernoulli, we have P1 divided by rho plus V1 squared divided by 2 plus GZ is equal to P2 divided by rho plus V2 squared divided by 2 plus GZ2. Forgot the GZ1 on the left-hand side. Okay. All right, so I am putting this in a slightly different form. So I did divide the entire expression by density, just so it is a little bit easier to compare to our conservation of energy. Okay. Okay, so let's compare that to our Reynolds transport theorem for conservation of energy, but we're going to do it in a very specific scenario. So we're going to do it in a case where we have adiabatic flow, where we have steady conditions, and we only have a single inlet and outlet. Okay. All right, and so in those conditions, we have P in divided by rho plus V in squared divided by 2 plus G Z in plus the internal energy of the inlet flow, okay, multiplied by the density times V times negative V in times A in plus same things at the outlet. We have P out divided by rho plus V out squared divided by 2 plus G Z out plus E out times rho V out A out. I had to do this a lot today to keep zooming out just because the expression's so long. All right, and that all is equal to the mechanical work W dot shaft. Okay, good. All right, so obviously these two expressions are looking very similar, right? And so that's kind of an observation we made from the beginning, because these three first terms, the pressure term, the kinetic energy term, and the potential energy term, those look like they're taken straight from Bernoulli. Okay. In fact, we can get this to look even more like Bernoulli by moving those terms over to the other side of the equation. Okay, so if we take the inlet terms, just because we have this negative V in here, if we move that over to the side, okay, we end up with the following, okay? All right. And let's also do this as well. So let's say by conservation of mass, the mass flow rate, m dot, has to be the same at the inlet and the outlet. So this is going to be equal to rho times V in times A in, which has to be equal to rho times V out times A out. Okay. Because remember, for a single inlet, single outlet system, assuming steady conditions, then all the fluid that comes in has to go out as well. Okay. Okay. And so if we do that and we move that over to the other side, what we get is on the left-hand side, we're going to have E out divided by rho plus V out squared divided by 2 plus G Z out plus E out multiplied by m dot. Okay, so we basically substitute that the carrying terms with the mass flow rate. Okay, this is equal to W dot shaft plus everything at the inlet. So we have P in divided by rho plus V in squared divided by 2 plus G Z in plus E in multiplied by mass flow rate. Okay. So what I'm going to do now is I'm going to divide this entire expression by m dot, just so that we can get it to be in the same form as Bernoulli. Okay. Okay, so that's going to eliminate m dot from both the inflow and outflow terms. It is going to change the units of our shaft work, but you're going to see it's kind of inconsequential at the end. Okay. I'm going to do one more thing just to get this in terms of Bernoulli as well. I'm going to take the internal energy at the outlet, E out. Okay. I'm going to move that over to the other side of the equation as well. Okay. Just so that, what you're going to see is that we're going to arrive at what I call the modified Bernoulli equation, which is the same as our original Bernoulli, but with just a few added terms to account for some additional things that Bernoulli did not account for before. Okay. All right. So if we do that, you get E out divided by rho plus V out squared divided by 2 plus GZ out is equal to E in divided by rho plus V in squared divided by 2 plus GZ in plus W dot shaft divided by M dot plus E in minus E out. All right, so what we have here is what I call the modified Bernoulli equation. Or I guess another way you can say it's called the extended Bernoulli equation. Okay, so they're both valid. Right, so you can see this, we have all the familiar faces with Bernoulli. We have our pressure term, our kinetic energy, our potential energy, but we have these additional terms here on the right. Okay. But first we have this term. So obviously this term here accounts for any kind of mechanical work or mechanical energy that we're either adding to the fluid or removing from the fluid. And the fact that we divide by m dot means that this is the mechanical work. Instead of being the units of power, this is going to have units of energy per mass. Right, so a little bit different units. So just be careful of that when you're using this extended Bernoulli or modified Bernoulli. Okay, so when you're using our conservation of energy in its in its base form, we get units of power. But because we divide by the mass flow rate, we get energy per mass instead of this. Okay. The other thing that we get, which is kind of the more important part, is these guys here. The difference in internal energy at the inlet and the outlet, E in minus E out. Okay. These are what we call our loss terms. Okay. So any kind of losses or energy losses that may occur due to viscous dissipation, those get accounted for in that internal energy. Okay. Okay, and so with this modified Bernoulli equation, we can tackle more situations with Bernoulli that we may not have done before. Okay, specifically, we can cover cases now that have any kind of viscosity. Okay, because before we couldn't do viscosity because viscosity led to losses, right? But now we can do that as well. Okay, and that's actually quite powerful, right? And so that allows us to cover a lot more situations than we did before. All right, so I have one example here. This is kind of a cool example because it's actually it's about something that you see or use maybe every day, which is a house fan. Okay, and we're going to use the modified Bernoulli to cover that situation. All right, any questions on this before we jump into that example? Okay, all right, so let's go ahead and do our example here. Okay, so let's consider a house fan. All right, so a house fan, is designed to basically turn and spin to generate airflow. Usually it's great on a hot day like this to kind of cool you off. Okay, so a fan like this, it's turning, okay? And by turning, it's generating airflow, right? So air is going to come off just like this. All right, so we're not going to do a control volume here, right? So just because, this is kind of a strange situation to have a control volume. Instead, we're going to analyze this like it's Bernoulli's. And so we're going to take one point here, and maybe we'll move that point a little bit closer. Okay, so we'll put a point right next to the fan. We'll call that point number 2. Okay, and we'll put another point here, and we'll call this point number 1. Okay. Okay. So we're going to place these points very intentionally, right? So if you remember in Bernoulli, a lot of times we placed a point at a location where air is completely still. Okay, and so that's what we're going to do at point 1. Okay, so we're going to assume that point 1 is so far away that the velocity there is very small. Okay, we're going to say that v1 is equal to 0. We're also going to consider the fact that since location 1 here is exposed to atmospheric air, its gauge pressure will also be zero there as well. Okay, so P1 is equal to zero. Okay. And so location two is right past the fan, right? So location two is going to have a velocity. We're going to say V2 is equal to 12 meters per second. But since location two is also exposed to atmospheric air, we're going to say P2 is equal to 0. All right, so other pieces of information that are given to us in the problem, since we're working with air, the density of air is 1.23 kilograms per meter cubed. Okay. Right, and we're also going to assume that the diameter of the fan, the diameter of the fan, sorry, is 0.6 meters. Okay. Oh, sorry, one more piece of information. Okay. So we know just based on the fan that we purchased and the power settings that the fan has, we know the fan requires 0.4 kilowatts of power in order to maintain this flow. Okay. So based on all that information, let's go ahead and compute. Okay. It seems like we have everything already, right? So we know kind of the velocities, we know the area of the fan, we know how much power it's consuming. Okay. But, we know that this fan is not going to be 100% efficient, okay? Because if this fan were 100% efficient, then all of the 0.4 kilowatts of power would be going into accelerating the flow, okay? But we know that's not the case because, we are considering viscosity, we're considering losses, okay? All right, so what we want to compute is we want to compute the energy losses. We're going to compute the energy losses in this situation, okay? And then based on those losses, we're going to compute the energy efficiency of the fan. So the efficiency being defined as how much useful work are we getting out of the power that's being put in. Okay. Right. So if you remember from your thermodynamics class, every type of device here that utilizes power has something defined as its efficiency. Which efficiency is the percentage of power that gets put in that gets actually used for something useful, right? That doesn't just get dissipated as heat or just result in some kind of losses. Okay. All right, so we do expect the efficiency to be fairly high because the fan is not necessarily a complex device, and so the losses should be fairly minimal. But let's go through the calculations just to make sure. Okay. All right, any questions on this before we if we start solving? Okay, good. All right, so let's go ahead and plug in. Right, so with this situation right here, the way it's defined, right? So we don't have a control volume here. We just have two distinct points. This is the perfect candidate for us to use our modified renewable. Okay. So since we don't have a control volume for this problem, not that we can't draw one, we can certainly draw one. But I think the more important point is that the problem specifically asked us for losses, which is something that we can directly solve for in our extended or modified Bernoulli. Okay, so our modified Bernoulli looks like the following. So we have P out, rho plus V out squared divided by 2 plus G C out is equal to B in divided by rho plus B in squared divided by 2 plus GZ in plus W dot shaft minus losses. Okay. So I'm kind of generalizing that difference in internal energy. Remember, the way we got that loss term was just internal energy in minus internal energy at the outlet. I'm just generalizing it as a loss term just so we can solve for it directly in our equation. Okay. Oh, sorry. W dot shaft here is divided by the mass flow rate. Let's not forget that. Okay. All right. So just like we typically do with Bernoulli, let's go ahead and cancel out some terms here. All right. So first thing we know, right? We know that both of our points that we chose, point 1 and point 2, are at atmospheric pressure. So because they're at gauge pressure, then there's no difference in pressure between them. So P out minus P in is equal to 0. Okay. We also know that the 2 points that we selected are at the same height. And so that means our gravity term is also going to be 0 as well. Okay. The last thing that we note is that our location 1, which is our inlet, is at still air, right? And so because we're at still air, the velocity at the inlet, or V1, is equal to 0. Okay, so that's the only one that's kind of not obvious, so we'll go ahead and write that in. Okay, so that means we get a very simple equation for our losses. And so our losses is equal to, I'm going to move the loss over to the other side, and then the V squared divided by 2 moving over to that side. Okay, W dot shaft divided by M dot minus V out squared divided by 2. Okay. All right, so we have most of everything that in this problem here, right? So we know the velocity at the outlet, right? So that's V2. That was 12 meters per second, right? In the problem, we're also given the power input for the fan itself, right? So the 0.4 kilowatts. Okay. The only piece of information that we're missing here is the mass flow rate, m dot. Okay. So let's go ahead and compute that. Okay. So we're going to compute the mass flow rate based on the outlet velocity V2 and the diameter of the fan. Okay. So again, even though we technically don't have a control volume, we can compute the mass flow rate of air passing through the fan because we know the diameter of the fan and we know the velocity of the air coming in. Okay. Okay. So m dot is equal to rho times the velocity times the area, right? Same as before. Where the area in this case is pi over 4 d fan, the diameter of the fan squared. Okay, so we go ahead and plug into this, and so what we get is 4.17 kilograms per second. Okay. Okay. All right, so we go ahead and plug all that in, right? I'm gonna do this so normally we can just kind of plug everything in here, but I am gonna plug in just one thing first, just because we are gonna use that in a second. Okay. Let's plug in W shaft divided by M dot. Right, because this quantity right here, you can think of this as kind of the amount of input power per mass that we're inputting. Okay, so W dot shaft as given to us in the problem was 0.4 kilowatts, 400 watts. Okay. And so we divide that by the mass flow rate, and what we get from this is 95.85 joules per kilogram. Okay. All right, so let's go ahead and plug that in and solve for the losses, right? And so we get loss is equal to W dot shaft divided by M dot minus V2 squared divided by 2. And what we get from that is 23.85 joules per kilogram. All right, so what that tells us is that for every kilogram of air that passes through the fan, we're losing almost 24 joules of energy just by viscous losses by heat. Okay. Okay. Any questions on this example so far? Okay, good. All right, so that's the losses, right? So next thing we want to compute is the efficiency. So remember, efficiency is defined as the percentage of work that gets put into the system that actually gets used for something useful, okay, that doesn't end up in losses. Which in this case, something useful is defined as accelerating the airflow, okay? Right, because we know the fan is putting in 0.4 kilowatts of power, right? But not all of that power is getting used to accelerate the air, right? In fact, we just computed it, right? So we just computed that 23.85 joules per every kilogram of air just gets lost, right? So that just gets, viscous dissipation that turns to heat, okay? Which heat in this context is not useful, okay? Okay, so to compute the efficiency, there is an equation for it. Right, so efficiency, usually I use the symbol eta here, which is just an N with a very long snout, I guess you can say. Okay. Right, so typically efficiency is defined as work dot in minus the losses divided by work dot in. Okay. Where in this case, W dot in is our shaft work, that is the work from the fan. Okay. All right, and so you can actually compute this as fractions, right? And so this is actually 1 minus the losses divided by W dot in. So we have everything here, right? The only thing you have to be careful of is that when you're computing that ratio of the losses divided by work done in, you want to make sure that they are in the same units, right? Otherwise, it wouldn't make sense, right? So our losses, as we just computed, our losses is 23.85 joules per kilogram. Okay. And our input work, right? Remember, we computed this explicitly, was 95.85 joules per kilogram. Okay. All right, so we plug all that in, and then what we get is an efficiency of 0.752. Or in other words, we have an efficiency of 75.2%. Okay, so only about 3/4 of the power that gets input into the fan is actually used to blow the air, right? 25% of it actually just gets lost, right? And so because of viscous effects, because of friction, because of maybe inefficiencies in the drivetrain of the fan itself, right? We lose about 25% just to heat. Okay. And heat, necessarily is not a bad thing. Sometimes you do want to heat the air, right? If it's a cold winter day, you want to turn on your heater. But usually this amount of energy that's going to heat is usually so minuscule that you don't actually feel it. Okay. Heating and cooling actually require a very substantial amount of energy, as probably you've discovered in your thermodynamics class. And so a very small amount of energy like this, like only 24 joules per kilogram, is almost imperceptible, right? So you can't even notice that difference. Okay. So that small amount of energy loss is just inefficiencies in the system that you don't even you pay for it, right? So you pay for the power, but you don't get to enjoy it much at all. All right, any questions on this example here? Okay, all right, good. All right, so we have about 35 more minutes left in class, and so this is actually the perfect amount of time to do conservation of angular momentum. Because there is one part, so I think it's part C of problem 5 on the homework, where you do need conservation of angular momentum in order to do. Okay, so again, we're not going to cover everything with angular momentum. We just don't have the time for it. But I do want to cover enough so that you can do that part of the homework. Okay. There was one more example with the modified Bernoulli equation. It was finally the example where we actually get to see some differences in height that I've kind of been promising you for a while. So unfortunately, we are skipping it again just because I think it's more useful for us to do angular momentum. But if you do want to see that example, it is at the end of the lecture notes. So if you go to lecture note 06, that was posted for today, just scroll all the way to the end, and then there's that example. It's not very long. It's actually the shortest example. But just going through the explanation and explaining will probably take another 15-20 minutes. But I think it's better for us to do angular momentum. Okay. Okay. All right. So this will be the last conservation law that we're going to use with Reynolds transport. Okay. Okay. So just like we did with energy, we're going to apply our conservation of angular momentum to, we're going to apply Reynolds transport theorem to conservation of angular momentum. Okay. And remember the two things that we have to do to apply RTT to a new quantity, right? We have to define our intensive quantity B. Because that's what we're going to plug into our general form of our RTT. And then the other thing is based on our selection for B, we're going to select, or we're going to write out what our production term looks like. Okay. All right, so this is going to look a little bit scary just because there is a cross product. But don't fret. I think you'll see from the example that when you do these problems in 2D, the cross product kind of gets canceled out. Right? Okay. So B. So little b for angular momentum is going to be the angular momentum per mass of the fluid. So in this case, B is going to be equal to the cross product of R, which is a moment arm, cross product with the fluid velocity. Okay. All right, and then our production term, right? So what are ways that we can generate, or what are ways that we can destroy angular momentum? Okay, so angular momentum is kind of just the angular analog of linear momentum, where for linear momentum, the way that we could produce momentum would be to apply an external force. Okay, so an external force could be used to either accelerate the flow, or it could be used to decelerate the flow. Okay, so the angular counterpart for that will be some kind of external moment. All right, so our production term in this case. Okay. So we have the material derivative of our expensive quantity for a system. For angular momentum, this is equal to the sum of any external moments on our system. Okay, so let's go ahead and put it all together, right? So let's go ahead and plug both of these into our general Reynolds transport theorem. And just like we've been doing, let's go ahead and assume steady conditions. Okay. All right, so remember, assuming steady conditions is going to eliminate our accumulation term, right? So the term with the partial derivative with respect to time. Okay. Okay, and so doing so, we get the following. We get integral of density multiplied by our cross product here, cross product of the moment arm, cross product with the fluid velocity, okay, multiplied by our fluid velocity dot product with the normal vector, so our carrying velocity dA. Actually, let me do this just to be consistent. Okay. I keep wanting to revert to U because U for velocity is kind of the that's kind of the standard that our textbook uses, but just for this class, I've been using V vector for velocity. So let's keep the same, just so you know that this velocity in the angular momentum is no different. Okay. So we have integral of rho times cross product of R and our fluid velocity V multiplied by our carrying velocity V dot product with n hat dA. This is equal to sum of all of the external moments. Okay, so this is the conservation of angular momentum on a control ball. Okay. All right. So in a lot of ways, this equation here is not that different than what we've been doing, right? And so it's basically the same inflow outflow term. We have a different production term, but moments are usually not that complicated. I think the thing that's intimidating and the thing that kind of trip people up is how we compute that cross product term like this. Okay. But like I mentioned, most of the time we're going to be doing our problems in 2D essentially. And so that cross product term will just end up being very simple to evaluate. In fact, most of the time, you're not even going to compute a cross product at all, right? And so that term just ends up being the product of the fluid velocity and the momentum of that fluid velocity. That ended up being a little bit of a bigger note than I anticipated. But you'll see in the example, right? So I think when people see vector operations, cross product, dot products, I know it looks a little bit intimidating, but when you actually go to apply it and you kind of understand why that cross product is there, it ends up being fairly simple to compute. Okay. All right. Any examples? Any questions on this before we jump into our last example for the day? Okay. All right, let's do one more example with angular momentum, and then we will wrap it up for. Okay. Okay, so for our last example of today, let's look at a rotating sprinkler head. All right, so if you open up lecture notes 06, this is actually the first example that you'll come across in that lecture notes. Okay. Okay, so I'm going to draw. Let's start with the aerial view here. Okay, so this is viewing the sprinkler head from the top down. Okay, so the sprinkler head has kind of two spigots. Right, so we have one spigot that looks kind of like this. Okay. And it comes into kind of a central piece, just like this. And then we have another spigot that's kind of coming around the outside, just like that. Just like that. Okay. All right. And then this is accompanied by the frontal view. So for the most part, we're going to use the top view. That's the one that's a bit more useful, but it's useful to kind of know where this comes from. Okay. All right. So if you've ever seen one of these rotating sprinkler heads, they're not that common nowadays, mostly just because they're kind of wildly inefficient with water. Normally, you kind of see the spraying type sprinklers nowadays. Okay. But it's basically kind of a spinning kind of head on top of kind of a post. So a post that kind of comes up just like this. Okay. And then we have our sprinkler head that kind of come around just like. Kind of a poor drawing. Let me kind of make it a little bit better. So remember, the sprinkler heads they're not facing up. They're kind of facing kind of horizontal here. Right, and so what's going to happen here is that water is going to come in from the base, right? So the base of this sprinkler head is going to come. There's a hose attached there. Okay, we have water that's coming in. Right, so there's going to be a volumetric flow rate of water coming in, and then that water is going to come up, and it kind of is going to come out of the sprinkler heads. Okay, so let's put some numbers on this, and so. All right, so the flow rate of water coming in. Okay, so that's given to us as 0.001 meters cubed per second. Okay, so that's the amount of water that's coming in from the hose up from the base coming out. Okay. All right, and so at the outlets for the sprinkler, so for both of the sprinkler heads, okay, we know their outlet area. So the outlet areas for the sprinkler heads is 3 times 10 to the minus 5 meters squared. Okay. All right, and then we also know the length of the sprinkler heads itself, relative to the where the rotating part is. Okay. All right, so we know this distance here. So this distance here, R, is equal to 0.2 meters. Okay. All right, so we're going to use that R there to compute our angular momentum. All right, so this is actually a multi-part problem. So there's actually 3 parts of this problem in the notes. We're only going to do part A because part A is the stationary control volume problem. We can also consider this as a moving control volume where the sprinkler head is actually rotating and spinning. But I think we don't have time for that. So I'm just going to focus on part A because that's all you need for the homework as well. Okay, so let's compute. Okay, so let's compute the torque that's needed. Right. So assuming that this sprinkler is in full operation, so there's water coming in and then the water is kind of spinning around, right? But let's assume that this sprinkler is locked, right? And so when the sprinkler is locked, there's a torque that the sprinkler needs to apply to the flow to prevent the entire thing from spinning. Okay? Or in other words, we're gonna consider the case where our control volume or a sprinkler is completely still. Okay. All right, so any questions on just the setup of the problem based on kind of what we're given here? Okay. All right, so right away, based on what the problem is asking us to find, right, so the problem is asking us to solve for torque. Okay. All right, so anytime you see torque, anytime you see moment, that's kind of a dead giveaway that you need to solve angular momentum. There's no other way to obtain torque in our equations that we've done so far, right? So we can't get it from mass, we can't get it from linear momentum, we can't get it from energy. So the only way we can get torque is from angular momentum. Okay. All right, so but first, before we do that, right, one thing you should notice is that we actually are not given the velocity of the fluid at the outlet. Okay, so let's go ahead and solve for that first. And the way that we can solve for that is by conservation of mass. Because that's the most handy way in order to do that. Okay, so first let's also make note. So in this situation, we have a single inlet, right? So water is coming in just from the hose from the bottom, but we have 2 outlets. Now our outlets are identical, right? So that does help us, but let's remember kind of how many outlets that we have. Okay, so conservation of mass in a steady case. what we get from that is integral of rho times v dot n hat dA is equal to 0. So that's our Reynolds transport theorem applied for mass for this control volume. Okay, so let's go ahead and evaluate this. And so we have rho Vn times A in, okay, minus sign. The minus sign is the fact that this is an inlet, okay, plus rho V out, A out. That's our first outlet. And then plus rho V out, A out. All is equal to 0. Okay, good. So first thing we notice here is that our density we're assuming is going to be the same at the inlet and the outlet. And since the right-hand side here is equal to 0, we can go ahead and factor out the density and just cancel it out. Right, so that density is going to go away, that density is going to go away, that density is going to go away. Okay. Okay. Other thing that we notice here is that we don't know the velocity or the area at the inlet, but we are given the volumetric flow rate at the inlet itself. Okay. Okay, so even though we don't know AN, we don't know VN, we do know their product, right? So their product QN, which is the product of VN and AN, right? So let's just plug in QN in for that. Okay. Good. All right, so we do that, we get minus Q in plus V out, A out, plus V out, A out is equal to 0. Okay. Right, for the first V out, A out, that's for the first outlet, and the second V out, A out is for the second out. Okay. All right, so we've already kind of implied this just based on the way I've written this, but because our two outlets have the same area, and they're the same kind of distance away from the middle, although that's a lesser factor. We can kind of reasonably assume that the two V outs are going to be the same. That's usually pretty reasonable to assume. Okay? Right, so essentially we're making use of symmetry in this problem to simplify it for us. Okay. And so if we do that, we get, and I'm going to go ahead and move Q into the other side of the equation, we get 2V out, A out is equal to Q in. Okay. So therefore, V out is equal to Q in divided by 2A out. Okay. Is equal to 16.67 meters per second. All right, any questions on how we got to this point here? Okay, good. All right, so we have everything that we need from conservation of mass, and so there's nothing more that we can apply from there. Right, so now we're ready to move on to conservation of angular momentum. All right, so our conservation of angular momentum equation is integral r crossed with v times v dot with n hat times the density dA is equal to sum of all of the external moments. Okay, which in this case, we only have one external moment, which is the torque that we're looking for. Right, we're not given in the problem that there's the presence of any other torques, right? We just know that there's going to be a torque that's going to prevent this entire assembly from spinning. Okay. So the last thing we need to do here is we need to evaluate that term on the left. We need to evaluate that at every single inlet and outlet of our problem. Okay, so this is where things get a little bit tricky, but not too tricky. Just as long as you kind of have a good understanding of what a moment and torque is. Okay. Okay, so to produce a moment, remember you need two quantities, right? So you need some kind of velocity vector, and you also need its moment arm. Okay. And so with that in mind, before you start evaluating this term, it's always useful to take a moment and identify what your axis of rotation in your problem is going to be. Okay. All right, so for this problem, if you look at the front view, spell front. Right, we know that our sprinkler kind of looks like the following, right? Now, I know for this part of the problem, we're looking for our sprinkler is stationary, right? It's not actually going to be moving, but there is going to be a natural way that it's going to want to rotate. Okay. Okay, and the way that's going to want to rotate, actually, this is kind of the worst view for it, but it's going to want to rotate like this, right? Right. So once water starts coming out, you can kind of imagine that's going to make kind of like a helicopter type of motion. Okay. That means our axis of rotation is right down the barrel or right down kind of the column of our sprinkler kind of middle column. Right, so just like we did with our hydrostatic problems, right? So for the hydrostatic problems, it was a little bit more obvious just because every hydrostatic problem there's a hinge, right? So that hinge was always our axis of rotation, right? But for these angular momentum control volume problems, sometimes you need to identify where that axis of rotation is. Okay. I think for the homework problem, for problem 5, there's a hinge, and so it's pretty obvious what the axis of rotation is, but sometimes it's not obvious. Sometimes you can identify. Okay. Okay. So once we identify the axis of rotation, right? For every single inlet and outlet for the flow, you need to be able to compute what the moment arm is going to be. Okay. Okay. So let's kind of remind ourselves very quickly what a moment arm is. So the moment arm is the perpendicular distance between the velocity vector and our axis of rotation. Because in order to cause a rotation, right, you have to kind of apply the force away from the axis of rotation. Okay. Okay. So for example, right? So if we're looking at this from the top down, right? So let's say this right here is our axis of rotation from viewed from the top. Okay. If we had a force or if we had a velocity that was, maybe acting like this, okay. Something like that is going to cause a rotation, right? Because if we compute the moment arm, remember, is the perpendicular distance. So that's basically the shortest distance that's perpendicular to our other vector that goes to the axis of rotation. Okay. So our perpendicular distance here is actually this. Should have drawn the vector a little bit longer. Right. So that right there is our moment arm. Notice how that line there is perpendicular to our other vector, right? So it's the shortest possible distance, right? So that's what we're going to use in that equation there. But you have to be careful because there are some vectors where maybe they're causing a force or maybe they're a velocity, but they may not contribute to the angular momentum. Okay. So the quintessential case for this is maybe you have a force or maybe you have a vector that's pointing right at the axis of rotation. Okay? We'll call this V2 here. So we have a velocity that points right at that axis. And so for these types of forces, for these types of vectors, right, we can't draw a moment arm here because the vector points right at the axis. So for these types, the moment arm is actually 0. So that's kind of an extra factor that you have to account for, okay? And so that's actually going to play a role here because one of the velocity vectors in our system, in our sprinkler system, is not going to contribute to the angular momentum, okay? Okay, so now that we're kind of done with that aside, let's go ahead and evaluate our angular momentum term here, okay? Okay, so first we have our contribution from the inlet, okay? So we have R crossed with V at the inlet, multiplied by our carrying velocity at the inlet, which is minus V in, rho A in, okay? Plus our contributions from the outlets. And I'm gonna go ahead and make use of our symmetry here, just to say that our two outlets are the same, okay? So you have 2 times R cross V out times carrying velocity, which is a positive V out, rho A out, is equal to our external, okay? Where I've kind of made that assumption here where our two outlets are the same. So I'm just taking the same contribution from the outlet and just multiplying it by 2. Okay. All right, so let's look at the inlet first. All right, so our inlet flow, if we go back up to the figure here, okay. I know I kind of draw it kind of weirdly here, but that inlet flow actually goes straight up kind of our axis of rotation, okay? And so because of that, we can say that our inlet flow here does not contribute to the angular momentum. Right, so what we're saying here is that because of the direction that the inlet flow goes up and because of our axis of rotation, okay, and so because of that, our inlet has no moment arm. And so actually this entire first term here, because of that, is going to be 0. But for the outlets is a different story. Because if we go back up to the figure here, right, we're given this distance here, which is actually the perfect perpendicular distance between the outlet nozzles and the axis of rotation, okay? And so that means this cross product contribution here for the outlets is going to be nothing more than V out multiplied by R, okay? Right, so in 2D, a cross product just ends up being just the product of those two things, okay? So again, if you're in 3D, the cross product is a little bit more complicated to compute, but in 2D, it is fairly straightforward, okay? Okay, but before we put a bow on this problem here, we do need to determine the sign of this cross product. Okay? So I just, maybe I just kind of lied just 20 seconds ago. So the cross product is a bit complicated because you do have to determine the sign. Okay. So just for the sake of time, I'll just kind of mention exactly how we determine the sign. So we determine the sign by the right-hand rule. All right, and so if you do the right-hand rule on those two vectors, you will see that the moment contribution or the cross product, you end up with a negative there. Okay. Right, so you can check the right-hand rule yourself to kind of verify that. All right, and so we put all that in and we are able to compute our external torque. So our external torque is equal to negative 2, excuse me, negative 2 times R times V out squared times the density times A out. Right, and so we have all those numbers there. We plug it in, we get minus 3.33 Newton meters. Right. Any questions on that before we wrap it up for today? Okay, all right, so that's everything with control volumes. And so we'll be right back at it again tomorrow. But tomorrow we're starting a new topic. But after today's lecture, you should have everything you need to do for homework. Okay, so tomorrow we're starting something new, but tomorrow's topic will be in homework 4, which is not going to be due until after the midterm exam. Okay, all right, so thank you guys for coming today. Hope you guys have a good evening. If you have questions on the homework, I've also started remember tomorrow before class. So don't be afraid to come to that or send me an email. But hope you guys have a good evening and I will see you guys tomorrow.
I think we're going to be having till it's back.
So exam 2 is not going to be cumulative. So the hydrostatic stuff in Bernoulli is not going to be on. So exam 2 will just be
Like, so like everything.
exactly. Yeah. So I'll put out a study guide tomorrow. Cool.
Really well.
So everything up to today is going to be on exam 2 for next year.
Exactly, yeah, so this is the cutoff for exam 2. Yeah,
Thanks.
yeah. Yeah.
So based on this, you think I could graduate by some?
Yeah, so you're enrolled in senior design for next semester?
Yeah, so fall I'm taking the dynamics, uh, tech elective, so senior design and 401. So that leaves just a lot of these ones.
Yeah, was you're in the dynamics control side?
I
Because the prerequisite for that is 360B.
So that I think that might be the one I need.
Okay,
So I applied for a heat transfer, but I don't know if I can take it because I'm probably gonna be working by then.
gotcha.
So I don't know if that's gonna work.
Gotcha. Okay. Yeah. So then you would take the heat transfer next spring. So it'd be spring 27. And then you take these 2 labs over the summer. Spring 27.
Do you know-
Summer 27.
You know if they would offer for
Yes.
tuition?
Yeah. We always offer those labs over summer just because,
Okay.
yeah. So typically the way we advise students is that we try to get students into senior design kind of as soon as possible.
Mhm.
Just because senior design is a year-long commitment. And you
Yeah.
have to take that in the fall and spring. So
Mhm.
that one's not flexible at all.
Okay.
And so what tends to happen is that students kind of fall behind with the fluids and heat transfer,
Mhm.
which is very normal. I'd say almost half of our students are like that now. And kind of the bottleneck here is because of 306B,
Mhm.
that's the prerequisite for these 2 labs here. And so students usually are taking fluids and heat transfer alongside senior design, then that prevents them from taking these labs in their senior year. And so we have like 50, 60 students every summer that need these 2 labs. And so instead of having you wait another full year to take these 2 labs, we offer it over summer, just so you can take them over summer.
So if for the summer classes for these 2, would it be like a 1-month program? Like
Exactly. Yeah. So they're both in session A, actually.
Oh, so you can't take one and then the next one after.
Nope, they're both in the same session.
Gotcha.
So in some sense, it's good because you kind of just get it over with.
Mhm.
But it is a little bit intense because it's a lot of labs and a lot of writing in a month. But the instructors also know that, so they know that a lot of students are taking both labs, and so they do account for that when they're assigning work for those labs.
Do you know if there's any chance of heat transfer going back in summer or after this class?
It might be. So we actually did try it for this summer, but there was kind of a snafu with the registrar because because this class is a prereq for heat transfer, so you need to complete this one first. So the way we set it up was we had fluids in session A and heat transfer session B, which is the one right after. But the registrar didn't recognize that. So everyone that signed up for this class, they tried to sign up for heat transfer,
And it would have
that we wouldn't let them because the registrar prevented that. So we'll probably have a conversation with the registrar next year. Because we try to have that conversation with them this year, but they were not helpful.
Okay.
Just
So
like
it's not coming back this summer.
not coming back this summer.
Okay, gotcha.
Yeah.
Okay.
Yeah.
Okay, so theoretically I would finish after summer, so graduate in like fall technically.
You'd graduate in the summer. So you would walk in the spring. So your commencement ceremony would be spring
But that
27.
would just take classes after.
Exactly. Yeah.
Gotcha. Okay.
But your diploma will be mailed to you probably September 2027.
Okay,
Yeah.
gotcha.
But technically you'll finish all your degree requirements by July 2027. So you can start your full-time job right after that.
Okay.
Yeah.
And then I had a question for the tech elective.
Yes.
So I don't know if that would require me to stay another semester. Because right now, I think for fall, I don't have anything lined up on my
Okay.
classes. For
Yeah,
tech.
and your options are probably limited because a lot of our tech electives require fluids and heat transfer,
Yeah.
right? Yeah, so yeah, I know you're looking at finite elements, so finite elements is a good option.
Because I'm on your wait list, but then I just checked again and it's like wait list is almost filled. There's only one open spot left.
Yeah, I know, yeah,
So-
yeah, finite elements is pretty popular. There are other courses, and so one course that I think not a lot of people know about is EGGN 403. So it's actually not in mechanical engineering, so it's under general engineering. So this one does count as an elective, and this one you should be able to take
Okay.
because you're
And what class is that?
So this is called numerical methods. So it is programming, and so it is MATLAB again. But it is one that you can take, and there's always open spots for it because no one knows about it because no one knows about EGGN. But yeah, that's one that you can take, and so I would say I would probably grab that one for now.
Okay.
Just to have that on your plan. And then I have to see maybe we can take a look.
And I was gonna ask if like there are any electives towards more like drafting, engineering drafting, like
Yeah.
controllers and stuff.
Yeah, so there's a
Intro, but then I don't know what the next steps.